Time for us to do some problems involving decomposition of acceleration, what we might call a sub t and a sub n. How much of acceleration is going with motion? How much is going perpendicular to it? As always, it's important to practice. And this one I think requires a little bit of practice because there's a couple different ideas in play and things can be interesting. So if you're following along with the video, make use of the pause button. If you see a problem you're not sure how to do it, actually try it yourself first. See how far you can get. And if you ever need help, go ahead and grab me. I'm there, just need to unpause me. Together, we'll make it through. Well, I think we should begin. So our very first problem, find t of t. Okay, so it probably is helpful to remind ourselves what is t of t. So t of t is notation for unit tangent vector. And what do we have? Well, we have a position, r of t. And so we say, okay, r of t is this 1/2 t squared, root 2 times t, log of t. So how do we go about computing the unit tangent vector? It is r prime over the magnitude of r prime. That's just what it represents. So there's sort of a couple steps. Find r prime, find its magnitude, divide, and we're done. That doesn't sound so bad. I think we can do it. I have faith. So let's start with the step 1. What is r prime? So we have the following. R prime of t is entry by entry, right? So t, comma, square root of 2. Interesting. And 1 over t. All right, now the next thing for us to do is talk about the magnitude of r prime. So the magnitude of r prime would be the square root of t squared plus square root of 2 squared plus 1 over t squared. Okay, now what would we like to be true? The ideal thing, the best case scenario, what is it? Well, what we'd like to be true is to have the inside simplify nicely. It won't always. We have to be honest with ourselves. If you write down a random function, it probably won't. But I suspect they aren't giving us random functions, so let's think about it. I see here the coefficients are kind of very suggestive. 1, 2, 1. It says maybe it's a perfect square. If we think of this as a squared, think this as b squared, the question is this 2ab? Well, if you look, if you times t by 1 over t, you actually get 1. So it is 2ab. So it's like, wow, this is the same as the square root of t plus 1 over t quantity squared. Or simplifying t plus 1 over t. We can also write that, if we combine, as t squared plus 1 over t. Now, that's our magnitude. So, what do we have? Well, we have the following. We put it all together. We can say our unit tangent vector, that's r prime over the magnitude of r prime. Well, if you divide by the magnitude, it's the same as multiplying by the reciprocal. So, t over t squared plus 1 times, and now you write down what you have. You have t root 2 and 1 over t. You could leave it as that. You don't have to go any further. But if we wanted to, we could then distribute through. So let's go ahead and just do that. Why not for this one time? So we end up with t squared over t squared plus 1, comma, square root of 2t over t squared plus 1, comma, and here the t's cancel, 1 over t squared plus 1. And we're done. It simplifies beautifully. Now there is kind of a small check that you can have. Namely, if it's a unit tangent vector, that means that the total length of the vector is 1. And if the total length of the vector is 1, no single entry can be large. In other words, no entry can be bigger in size than size 1. And here you can go through, won't do the verification of everything, but you can see, for example, 1 over t squared plus 1, that's certainly smaller than 1. See, the denominator is larger. Similar, t squared over t squared plus 1, the denominator is larger. Maybe it's not so clear for square root of 2 times t over t squared plus 1, but it does turn out that, lo and behold, this is also a case where it's always bounded. Now, you might be a little bit suspicious here if you've been watching a lot of these videos, saying, look, Steve, you've burned me in the past with the square root of something squared. How did you know that you didn't need an absolute value there? Ooh, you're asking some good questions. How did we know that we didn't need an absolute value there? The answer is I kind of hid a small detail. If you look at the way the problem is stated, look up here, log of t. It's log of just t. Now, what numbers can you plug into t? The answer is you can only plug in positive numbers. So because of the way the problem is stated, there's this sort of implicit indicator that says, hey, t is positive. If we hadn't had that, then we would have to go through and be more careful. And we probably would need to have an absolute value of t floating around. But for now, we're safe. Good. All right. Well, one problem down. I suspect it's a warm-up. I think the next couple ones are going to be more interesting. Well, only one way to find out, and that's to actually do them. So let's go and do another problem. Here we go. Find a sub t and a sub n for the following. You have r of t as this big expression, and we want to find what happens with a sub t and a sub n. So since we're still learning, we said, hey, there's two ways to approach this. There's the algebraic and there's the geometric. Should we try both and see how we do? Why not? Then we can compare. And we can say, all right, I see what's going on here. I see some advantages one way versus another. So, regardless of what method we do, we always are going to need to have r double prime, magnitude of r prime. So we should always start with those three. So they're common to both. So let's start with r prime. So here we have the derivative of sine is cosine. Here, product rule, derivative of the first times the second, 1 times cosine. So minus cosine. Then minus the first times derivative of the second. Derivative of cosine, negative sine. So it becomes a plus sine, comma, derivative of the first minus sine. And actually, there's just one term. Here's the product rule. Derivative of the first, 1 times sine. So sine plus the first times the derivative of the second, cosine. And then t squared, derivative of that, 2t. Well, let's see. We can clean that up. And you should always clean things up. If you're going to do something with an expression, clean it up before you do anything with it. Because if you don't clean it up, you're just going to have sort of compounding complication of notation. You want to clean things up at the start. The sooner you clean something up, the better it is in the long run. So here, look, the cosines and the sines cancel. Wow. Cool. So this becomes t sine t, t cosine t, and 2 times t. Okay, so how about r double prime? Well, here we go. Derivative of the first times the second, sine t, plus the first times the derivative of the second, t cosine t, comma, derivative of the first times the second, cosine t, plus the first times the derivative of the second, Derivative of cosine being negative sign gets us to a minus t sine t. And the derivative of 2t is 2. Okay, and we need the magnitude of r prime. So, magnitude of r prime, that's the square root of, we square every term, t squared sine squared, t squared cosine squared, and here it'll be 4t squared. All right, well, we can certainly clean things up. Notice t squared sine squared plus t squared cosine squared becomes t squared. All right, good. And now, so we have 5t squared, so we'll write this as the square root of 5, and square root of t squared will be t. Let's go ahead, just for simplicity, I'm going to assume t is greater than or equal to 0. I'm not going to worry about what happens when t is negative. Okay, that way we don't have to stress too much about, what about absolute value? Okay, all right. Okay, good. Now, we have geometric or algebraic. Maybe we should do geometric first, because I think if we do algebraic first, we're not going to have the heart to do geometric. Okay, so when we're doing geometric, the next thing, after we've computed these things, we need to do the dot product and the cross product. So r prime dot r double prime. So we multiply the entries together. So we're going to get t sine t times sine t plus t cosine t. All right, just the first entries, plus t cosine t, and then we're going to multiply it by cosine t minus t sine t, and then we're going to have 2t, and we're going to multiply it by 2. So, if we work this out, we're going to get t sine squared, all right, and then t squared sine t cosine t. Interesting. Here we're going to get t cosine squared, all right. It has to be something. So, and then if we multiply this out, we say, aha, there's a minus t squared, and then there's a cosine t sine t, and a plus 4t. Good. Now, what do we have? Well, we say, hey, look, the t squared sine t cosine t, the minus t squared cosine t sine t, cancel. Life is good. But it gets better. Here, t sine squared, t cosine squared, put them together, we get t. Add 4t more, and we're up to a wonderful 5t. So, there we go. That's r prime dot r double prime. Beautiful. Okay, now, next up, the cross product. Okay, it's good to do a good cross product. It feels like it's been a while since we've done a really good one, right? So, r prime cross r double prime is I, j, k. Okay, so put in the entries of r prime. T sine t, t cosine t, 2t. You might be wondering, are we allowed to put functions into cross products? The answer is yes. I mean, because keep in mind that functions are really just saying, here's how something varies. You can always evaluate, and then you actually have numbers. And so you can put in functions. That's perfectly fine. No problem with that. Okay, and then of course we have sine t plus t cosine t, and we have cosine t minus t sine t, and then we have 2. Good. Now, depending on how much you know about cross products, you can do a little bit of simplification here, but I think it would cause more confusion than just doing it, so we're not going to do the simplification. For anybody who does know about determinants, I will say there's something you can do at this stage, which is you're always allowed to add a multiple of one row to another row, and it doesn't change the answer at all. So you could take this bottom row and multiply it by negative t and add it to the middle row. It wouldn't change your cross product at all, but boy, it'd be a much simpler computation. Well, at least a little bit simpler, I think. Who knows? Who knows? Okay. But for us, we forge ahead. Okay, so here we go. All right, for I, we have I times t cosine t times 2. So that's going to be 2t cosine t I. J times 2t times this expression here. So plus, we'll multiply it out, 2t sine t plus 2t squared cosine t. And that's j. And k, well, we're going to multiply the t sine t times that. So plus, well, it's going to be t sine t cosine t minus t squared sine squared t. Okay. Okay, that's going diagonals one way. We have to do diagonals the other way. All right, so going in the opposite direction. Well, we're going to subtract, and then I'm going to multiply the t cosine t through. So that's t cosine t sine t, and then there'll be a plus t squared cosine squared t. Okay. Cosine t minus t sine t times 2t I, but it's being subtracted. So I'm just going to write subtract, and then it's 2t cosine t and minus 2t squared sine t I. And finally, in the j, 2t sine t j. So minus 2t sine t j. Okay. Wow. Does anything simplify? Well, if we've lived a good, clean algebra life, things should simplify. Somehow something should get simpler at a stage. All right. Well, let's dig into it a little bit here, right? Okay, so what can we say? Well, here the 2t cosine t's and the I cancel. The 2t sine t's and the j cancel. And the t sine t cosine t's and the k cancel. So what are we left with? Well, we're left with here minus minus makes 2t squared sine t. That's an I, comma. We'll have 2t squared cosine t. That's in j. And then here, if you look, you have minus t squared sine squared minus t squared cosine squared. Well, that simplifies to give us minus t squared. Now, it's still the case that you can go ahead and check with the dot product. We'll do it with just one of them. This would be 2t cubed sine squared. That would be 2t cubed cosine squared. So if you put those together, that's 2t cubed. That's minus 2t cubed. That's 0. That's a promising sign that we did something right. The fact that we also got cancellation is also a promising sign that we did something right. Oftentimes that happens when you get sines and cosines involved. Now, what's next? Well, we need to find the magnitude of this. So, here we go with that. The magnitude of r prime cross r double prime would be the square root of, well, we square every piece. 4t to the fourth sine squared plus 4t to the fourth cosine squared plus t to the fourth. That's what we get when we square every term. Again, sine squared plus cosine squared equals 1. Aha, beautiful. Mwah. Really beautiful. And so that leaves us with 4t to the fourth plus t to the fourth, which makes this the square root of 5t to the fourth, which we can write as the square root of 5t squared. All right, now we put it all together. And here we go. So, our answers. We can put our answers right here into our box. A sub t is r prime dot r double prime over the magnitude of r prime. Well, that is 5t divided by the square root of 5 times t. The t's cancel. 5 over square root of 5 leaves us with square root of 5. Okay, that's not so bad. How about a sub n? Well, that's the magnitude of r prime cross r double prime over the magnitude of r prime. Okay, well, upstairs we have square root of 5 t squared. Downstairs, square root of 5 t, and that simplifies to t. So there's a sub t, and there's a sub n, and we're done. And you're probably thinking, I would hope so. There's a lot of stuff here. And that was the geometric. So remember, this part plus all of this is what you need to do if you're going to do it geometrically. Now let's switch gears. Let's do everything algebraically. Aha! We'll work in the corner. So you're probably thinking, you don't have enough space. Hold on. Okay, so let's use, let me find the color blue. Here's a blue one, just so we can sort of compare. All right, so once we have this, we say, look, if I want a sub t, that's the derivative of the magnitude of r prime. So that's the derivative of root 5 times t, which is root 5. Hey, they match. Well, of course they match. It's just two ways to compute the same thing. You're probably thinking, that was fast. We didn't have to do r prime dot r double prime. You are correct. What about a sub n? Okay, now for that, we do need to do a little bit more work that we didn't do down here, which is what is the magnitude of r double prime? So, okay, so here we go. Got to take the square root of these terms. So square root of the x term would be sine squared plus 2t sine t cosine t plus t squared cosine squared t. All right, I don't have enough space, so I'm going to write the next square underneath it. So plus cosine squared minus 2t sine t cosine t plus t squared sine squared t, and then plus 2 squared is 4. Okay, so that's the magnitude of r double prime. Now, what do you see? Well, we've lived a good, clean algebra life, meaning we get cancellation. Good. Sine squared plus cosine squared is 1. Plus 4 more gives us 5. Okay, so that's the square root of 5. And then t squared cosine squared, t squared sine squared is t squared. Now, here's the last part. We have that a sub n is the square root of the magnitude of r double prime squared minus a sub t squared. Well, that would be the square root of, if you square that, that's 5 plus t squared, subtract 5, because we square these terms. Well, that's the square root of t squared, also known as t. And they match. Perfect. Amazing. Well, we shouldn't be surprised that they match. Of course they would match. But I think what we'd be more surprised at is this was a lot faster. Look at how much space it took. It was like tiny compared to all of this. And every time you do a computation, of course, you expose yourself to a potential for making an error. So this is why if you have a choice and you're trying to solve it for a general t, most of the time it's a lot better to do it the algebraic way. But we'll come back and there'll be at least one point where we say, hey, I'm glad we remember that geometric can also work. Okay, good. Good. Progress. Well, let's do some more. All right, well, let's go to our next one. So, find a sub t and a sub n where you have r of t is e to the t plus 17, and 2e to the minus t plus pi, and 31 minus 2t, and determine all times when acceleration will be perpendicular to the direction of motion. Okay, so there's two parts, parts A and B. And we can talk about part B once we finish part A. So hopefully by the time we finish part A, we'll be like, aha, and part B is not so bad now. So let's start with our A sub t and A sub n. Again, let's do it both ways. In other words, geometric and algebraic. So we start by saying, okay, let's find our various pieces. So we'll start with r prime. So take the derivatives. That's e to the t, comma, minus 2, e to the minus t, comma, negative 2. Our double prime would be e to the t, and then we would be 2e to the minus t and 0. Okay, I can already feel like this is going to be a little bit simpler than the last problem. The terms weren't getting bigger and bigger. All right, we need the magnitude of r prime. Okay, magnitude of r prime. Okay, what would that be? That's the square root. Well, that's e to the t squared plus 4 e to the minus t squared and plus 4. Now what we'd like is for this to be a perfect square, because if this simplifies at all, then algebraic becomes super fast. Even if it doesn't simplify, algebraic's not so bad, but we think, okay, there's 3 terms here. Maybe it's a perfect square. In fact, there's sort of a hint. If you start hanging around perfect squares a lot, you start looking for coefficients like 1, 2, 1. That's a common pattern. Another very common pattern, 1, 4, 4. Now why do I say that? Well, if you take quantity a plus 2b squared, you get a squared plus 4ab plus 4b squared. So that's why when I see a 1, 4, 4, it's like, this could work, this could work. But I don't think it's in the right order. It looks like maybe if we did this, I think if you rearrange things, because I can see, here I can think of this as like 1 squared. The problem is, if I take the e to the t and the 1, I don't get e to the minus t. But if I take e to the t and e to the minus t, I do get 1. So let's think about it this way. It's like e to the t squared. If I think of this as sort of the last term, that would be 2e to the minus t squared. Then the middle term could be 2e to the t, 2e to the minus t. Let's see, does that work? We get 4. Yeah, that works. So that's the square root of e to the t plus 2e to the minus t squared, which is, I just want to save myself some space because I worry we have a lot to do in this problem. Okay, so there we go. There's our magnitude of r prime. And the good news is it's very clean, very clean. In other words, we got rid of the square root completely. Wow. When you do that, you're in great shape, and life is good. Now, here we transition. Let's do our geometric, and let's see where we go. So, do the dot product. R prime dot R double prime. Well, e to the t times e to the t would be e to the 2t. Minus 2e to the minus t, 2e to the minus t would be minus 4 e to the minus 2t. Whoops, that's not a vector. It's a number. We take a dot product and 0. Okay, so there we go. That's the dot product. And we're going to come back to this in a second, maybe in a few minutes, but okay. All right, now we'll do the cross product. R prime cross R double prime. What would that be? Well, that would be the following. We take our I, J, K, e to the t, minus 2 e to the minus t, minus 2 e to the t, 2e to the minus t, 0. And we start going. I times minus 2e to the minus t times 0, 0i. J times minus 2 times e to the t, minus 2 e to the t, j. K times e to the t times 2e to the minus t. Well, the e to the t and the e to the minus t actually cancel, so we're left with a 2 times k. Now, in the other direction, okay, e to the t minus 2e to the minus t times k. E to the t and e to the minus t still cancel, so it would be normally a minus 2, but we're going in the sort of opposite direction. Minus minus makes a plus 2. 2e to the minus t times minus 2 times I. Well, that's minus 4e to the minus t, but of course we're subtracting that, so it becomes a plus 4e to the minus t, and 0 times e to t times j is 0. So we get 4e to the minus t, comma, minus 2e to the t, comma, 4. Now, we can still check. It still works with our check. See, here, multiply, we get 4. Here, you'd get 4 again. Here, you get minus 8, 0. Down here, 4, minus 4, 0. It works. Clean. All right. Well, the other part we need is the magnitude of this cross product. So, magnitude, r prime cross r double prime. Well, that will be the square root of, okay, well, we might be here a while. Or, maybe not. We can actually save ourselves some work. Well, okay, let's pretend like we didn't see anything clever. We'll come back and point out something clever in a second. Okay, so you square the first term, 16e to the minus 2t, plus, square the second term, 4e to the 2t, and plus 16. And you say to this, wow, hey, this really, look, everything has a factor of 4, right? Well, yeah, everything does have a factor of 4. Okay, so how do we use that? Well, pull it out. Square root of 4 leaves us with 2. Then we have the square root of 4e to the minus 2t. And then here, plus e to the 2t, and plus 4. Now, if you rearrange, you can say, hey, this is equal to 2 square root of e to the t squared. Okay, that's this term in the middle. Plus 2 times e to the t times 2e to the minus t. And you're like, yeah, okay, and it is 4. Where are you going with this? And this would be 2e to the minus t squared. Which gets us to, this is really 2 times the square root of e to the t plus 2e to the minus t squared. You're like, oh, I'm getting some deja vu. You should be. So that's 2 times e to the t plus 2e to the minus t. And now you're like, that sounds a lot like the magnitude of r prime. Because now let's be clever. A little bit, not much, just a little bit. Notice here, if you pulled out a negative 2, what would you have? Minus 2e to the minus t from the first term, e to the t, and minus 2. Now, compare that to there. It's the same entries, just in a different order. When you take the magnitude, you basically don't care the order of the entries. So we should get the absolute value of negative 2, which is where the 2 comes from, and then the same thing that we got for the magnitude of r prime, because they are up to scrambling the same vector. Okay, all right, well, we now have to put it together. So, to get our answers, what do we have? Well, we have a sub t, that's r prime dot r double prime, over magnitude of r prime, which is what? Well, that's e to the 2t minus 4 e to the minus 2t divided by, and where's the magnitude of r prime? It's over here. E to the t plus 2e to the minus t. Okay, there we go. A sub n, magnitude of r prime cross r double prime over magnitude of r prime. Well, we know where it's going to happen. So we got a 2 e to the t plus 2e to the minus t divided by an e to the t plus 2e to the minus t, which gave us 2. All right. So there we go. A sub n looks really nice. A sub t, maybe. We'll come back to that in a second. Okay. Now, that was geometric. Let's do algebraic. And we'll work in the corner. Okay, so what do we need? Well, we have our magnitude of r prime. So a sub t, that's our derivative of e to the t plus 2e to the minus t. And that becomes e to the t minus 2e to the minus t. And now they're, wait, what? Shouldn't it be the same? Uh-oh. Uh-oh. What? What's happened? Are they the same? Okay. So here, I said we'd come back in a second. It took us longer than a second. It took us a couple minutes. But now we're back. This is kind of a fun little thing to notice. Notice the upstairs. It's actually two things which are squared. It's e to the t squared minus 2e to the minus t squared divided by e to the t plus 2e to the minus t. Now, a squared minus b squared is a minus b times a plus b. So this is a minus b, a plus b, divided by e to the t plus 2e to the minus t. And now you're like, oh, I see what's going on. These terms cancel, so it is indeed e to the t minus 2e to the minus t. Okay, good. All right, so there's our a sub t. That's a sub t. All right, let me just make that more t clear. What is our magnitude of r double prime? Well, actually, we'll just say, look, a sub n is the square root magnitude of r double prime squared minus r a sub t squared. Okay, so we got to figure out what that all becomes. Okay, so magnitude of r double prime squared. Well, that's going to be, you just square each term. So that's e to the 2t 4e to the minus 2t. Okay, that's no problem. Then we're going to subtract. We square that. Well, that'll be e to the 2t. That's the first term squared. The cross terms will be a minus 4, because e to the t and e to the minus t cancel. And then we're going to get a plus, square the last term, 4e to the minus 2t. All right. Well, you can see where we're going. The e to the 2t's cancel. The 4e to the minus 2t's cancel. Minus minus 4 makes the square root of 4, leaving us with 2. And we're done. And now you're like, wow, we got the same answers. But boy, it seemed a lot easier to do things algebraic, didn't it? Well, it does, yeah. Okay, now, part B. And you're probably thinking, there's no space left. How can we possibly finish up? Well, we'll try to squeeze it in somewhere. But we can figure this out. It says, determine all times when acceleration will be perpendicular to the direction of motion. Now, there's sort of two things you can do, and they're about the same amount of work. Now, one thing you could do is say, look, I just need to have motion and acceleration be perpendicular. So that really says what? That r prime dot r double prime equals 0. That sets up a formula. You solve it for t, and you're done. We kind of basically have that already, though. So there's another way to interpret this. We say, look, acceleration has two parts. So if I have my motion, I have a sub t, which is with motion, a sub n, which is perpendicular to motion. Now, if we want all of acceleration to be perpendicular, that says a sub n is everything, a sub t is nothing. So another way to think about this is it says, oh, set a sub t equal to 0. So that's what we can do. So if we take our a sub t, whoop, almost off the screen there, and if we set that equal to 0 and solve, well, what does that become? That becomes e to the t equals 2 over e to the t, right? Because I'm going to move that across, and e to the minus t is really 1 over e to the t. Or, as we keep running out of space, that's the same as saying, multiplying across, e to the 2t equals 2. Okay, this is great because now we're down to 1t, a single t. 1t to find them all, 1t to bind them, 1t to bring them all, and in the light of calculus, make it work. All right, take the log of both sides. 2t equals natural log of 2. And finally divide, and we get t as 1/2 log 2. So there's the answer for part B. So in some sense, you could say, look, I could just start from scratch. R prime dot R double prime equals 0. And if you do that, you just take this equation and you set it equal to 0, and you'll get the right answer. Or you say, hey, I did a lot of work, I found a sub t, and really this is the same as saying a sub t equals 0. Okay, great, just do that. And then you'll also get the right answer. You might be a little bit skeptical that says, well, does that also get to 1/2 log 2? And the answer is, yes, it does. It does work out. Just be careful with your properties of logs, and they are the same. Okay, that was a long problem. All right, well, probably we should do a different one. Here we go. Given that the position of a particle is given by this r of t, find a sub t and a sub n. In the interest of sanity, I think we can now say, look, we know the two methods both work. I think that probably by now we're leaning towards algebraic. Let's do this one all algebraic. We're going all in for algebraic. We're like, yes, shoving our calculus chips forward, and we're going all in. All right. Well, let's see what happens. So if we're doing things algebraically, we start with r prime, and we say, well, what is that? That's t to the 5th, comma, then 2 t to the 4th, comma, and 2t cubed. R double prime, 5 t to the 4th, comma, 8t cubed, comma, 6t squared. Okay, well, that's not so bad so far. Okay, well, what's next? Magnitude of r prime. Now, this is when we are crossing our fingers and saying, oh, please simplify in the square root. Please simplify in the square root. Please simplify in the square root. Well, let's find out. What is that? Okay, so that's the square root of, and what do we get? First term squared, so that's t to the 10th, plus here 4t to the 8th, and 4t to the 6th. Like, oh, that's kind of weird. Okay. All right. Well, what can we do? Well, we certainly can pull out a t to the 6th. So that's the square root of t to the 6th. Then we have t to the 4th plus 4t squared plus 4. And I think, boy, it's not a quadratic. It's a quartic, 4th degree. Or is it? Well, it depends how you look at things. Let's, for simplicity, we'll assume t is greater than or equal to 0. I just don't want the headache right now of saying, well, let's worry about absolute value. Forget it. It's not worth it. Okay, so what do we have? The square root of t to the 6 will be t cubed. Now, why do I say, look, it's really a quadratic? See, t to the 4th is really t squared squared. And then you have a 4t squared, and then you have a plus 4. So that is what? Well, it's really, if you play around with it, t squared plus 2 squared. Nice. So this is t cubed times t squared plus 2, or t to the 5th plus 2t cubed. Wonderful. This is the best possible scenario for us. Now we're ready to start answering at least one question. We can do a sub t now. So a sub t would be the derivative of t to the 5th plus 2t cubed. In other words, it's the derivative of the magnitude of r prime. Well, that's something we can compute. That's 5t to the 4th plus 6t squared. And now we're like, great, we did it. Okay, what about a sub n? Well, so a sub n is equal to the square root of magnitude of r double prime squared minus a sub t squared. Right? That's the formula. Take the magnitude of acceleration and divide by, subtract out a sub t quantity squared. All right, so what do we have? Well, so this is the square root of, go through it term by term, 25 t to the 8th, 64 t to the 6th, 36 t to the 4th. All right, that's just the magnitude of r double prime squared. Now we're going to subtract here a sub t squared. Okay, so that would be 25 t to the 8th. Ooh, I'm getting deja vu. 5 times 6 would be 30, but remember we've got to double it 2ab. So 60 t to the 6th and 36 t to the 4th. Okay, I'm like, wow, look, cancel, 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 cancel. 64 minus 60, that gives us the 4. So we get the square root of 4 t to the 6th, also known as 2t cubed. So there's our a sub t. There's our a sub n. Done. All done. It's beautiful. Beautiful. Wow. Great stuff. Great stuff. Good stuff. Okay. You'll notice there was nothing terribly hard or complicated about this. And, of course, that was because we were very patient, very methodical. Now, you might say, okay, so you're kind of cheating a little bit. You said t is greater than or equal to 0. What would happen if you said t is less than 0? What's the change? Well, not a big change, actually. You could even work it out. So if t is less than 0, you would say, look, the problem is this r prime, magnitude of r prime would be a negative value for negative values of t. So you would put negatives here, and then what happens? Well, that turns a sub t. You're going to have negatives there, but a sub n won't change. And so it's actually not so bad. So that's it, actually. So, all right, well, one more. One last problem. And for our last one, I think it's good to say, maybe we should go to geometric. Let's think about this problem first. Okay, so here we have this r of t, arctangent of t, I e to the minus tj sine squared of t plus 3tk. And it says find a sub t and a sub n at time 0. So it's not find it at some arbitrary time. In other words, we're not looking for functions of t. We want numbers. Okay. So in other words, we're going to do an evaluation. So how do we go about doing this? Well, you can do it really either way, but the question becomes, when can you evaluate? So if you think about the process, what do you have? For algebraic, we have the following. So, whoops, I can spell algebraic. Here we go. Algebraic. Well, step 1, we have to compute the r prime, r double prime. Step 2, we have to compute magnitude of r double prime. Step 3, we find the derivative of, it's just r prime, I'm sorry. Find the derivative of the magnitude of r prime. In other words, that's a sub t. And we could say step 4 is to say, okay, now we're going to find a sub n, which is the square root of the magnitude of r double prime minus a sub t squared. Okay, that's algebraic. Now, geometric. Let's compare. So what happens in geometric? We'll do a different color here. In geometric, what do we have? Well, step 1, we need to compute r prime, r double prime. Step 2, we need to compute the magnitude of r prime. Step 3, we need to find r prime dot r double prime, r prime cross r double prime, magnitude of r prime cross r double prime, and step 4, find a sub t, which is the dot product over the magnitude of r prime, and a sub n, which is the cross product over the magnitude of r prime. Okay, so that's sort of the two processes side by side. That's what you have to do. Now, the question becomes, when do you evaluate? Oftentimes when people see an evaluation problem, they say, okay, I know the answer to that. They say, this is where we evaluate. And you can say, well, it's true it would work, but if you evaluate here, it's going to be lots of work. Because you have to carry all of that information about the functions all the way through. So when can you evaluate? Well, the answer is you should always evaluate as soon as you can, but not sooner. So how do we know when we can do it? Well, the real question is there any point in a step further down that requires you to have knowledge about what the specific function is versus what the evaluation is? So here is where things get fun. Whenever we need to take a derivative, we have to have our function. We can't take derivatives of numbers, so we can't evaluate them, take a derivative, because we'd get 0. So if you take a look for algebraic, we cannot evaluate until right there. That's the soonest we could, because we still are taking derivatives before that step. That's as soon as we can evaluate. Whereas for geometric, right there, because that's it. After that, once we have r prime and r double prime, there's no more derivatives involved. Everything is about measurement of vectors or operations with vectors. And now, here's why the geometric wins the game for this type of problem. look how early in the process we get to evaluate. The sooner we get to evaluate, the sooner things collapse and become simpler. So, for this problem, where we have an evaluation, geometric has an edge because we get to evaluate so much sooner. So that's why on this problem, we're going geometric. Okay. Well, now that we did a lot of rambling there, let's actually go and finish the problem. So let's do this. We need r prime and r double prime. So what is r prime? Well, I'll just write in component form. Derivative of arctangent, 1 over 1 plus t squared. Derivative of e to the minus t, minus e to the minus t. Derivative of sine squared, 2 sine t, cosine t, and plus 3. Okay. And remember, if we were doing algebraic, we'd have to still compute the magnitude of this. We cannot evaluate yet. And so there'd be a square root of this squared plus that squared plus that squared. Take the derivative of that, and believe me, that square root will not simplify. And okay, so now you're like filling up lines after lines. Like, okay, here it is, here it is. Ah! So that's why we're not doing it. Okay. I'm not going to do it. You can try it if you want, but r double prime. All right, well, these aren't too bad. If you take the derivative here, one way to think of 1 over 1 plus t squared is you can say, hey, 1 over 1 plus t squared is the same as 1 plus t squared to the minus 1. So the minus 1 comes down, 1 plus t squared to the minus 2, which means there's a 1 plus t squared squared. Then the root of the inside is 2t. Don't forget the minus we first said, so minus 2t over 1 plus t squared squared. Second entry is e to the minus t. And the third entry, well, okay, you work it out. Root of the first times the second, so that's 2 cosine squared t. And then root of the first times root of the second would be minus 2 sine squared t. Root of 3 is 0. You could even simplify and say, hey, 2 times sine times cosine, that's sine of 2t. And that's actually even easier to work with. But we digress. Now we've computed r prime and r double prime. From here on, we're going to evaluate. So before we do anything else, we plug in 0. So what is r prime of 0? Well, it's 1 minus 1, 3. R double prime is 0. It is 0, 1, 2. And now we work with these quantities. Okay, what's the magnitude of r prime? Okay, so the magnitude of r prime of 0 is the square root of 1 plus 1 plus 9, which is square root of 11. Okay, well, had to be something. Okay, how about r prime is 0 dot r double prime is 0? Well, 1 times 0, 0, minus 1 times 1, minus 1, 3 times 2, 6. So we end up with 5. Okay. And see how easy this is? There's like no functions. These are just numbers. Life is good. Everybody's happy because that's what we want. We want people to be happy. Okay, good. Well, continuing on. Next up, we have to do the cross product, right? We found r prime dot r double prime. Okay, the cross product. So, r prime cross r double prime, that's I, j, k, 1 minus 1, 3, 0, 1, 2, minus 2i, 0j, plus k, minus 0k, minus 3i, and minus 2j, j. So that looks like minus 5, minus 2, 1. Well, let's check. Okay, minus 5, plus 2, plus 3. Good. 0, minus 2, plus 2. Good. Okay, so that's, we've taken the dot product, we've taken the cross product. The magnitude of -5, -2, 1 is the square root 25 plus 4 plus 1. So that's square root of 30. Okay, so we've done this, and this, and this, and this, and we did that at the beginning. So now we're just ready to write down our answers. So a sub t is, we have the dot product is 5 over the magnitude. So 5 over square root of 11. A sub n is magnitude of the cross product, square root of 30, divided by magnitude of r prime, square root of 11. And we're done. It wasn't so bad. It wasn't so bad at all. But of course we had to do the work. We had to do the work. Now, if we were paranoid, but of course we're not, we can do a couple of small checks. So for example, if you take a sub t squared and add a sub n squared, well, we should get the magnitude squared, right? So 5 over square root of 11, square that, that's 25 over 11. Here you square this, you get 30 over 11. That's 55 over 11, also known as 5. And that is indeed the magnitude squared. Okay, so it's not too surprising though. It should work out. But again, you see, because we went with geometric, we took advantage of the fact that evaluation could happen really close to the start, meaning that all the computation after that could be done with just vectors, which makes things a lot easier to work with. Whereas if we had an algebraic, brutal, because we'd have to wait quite a while before we evaluate. All right, well, good. Well, we've had a lot of fun, and I hope we learned a lot along the way as we did our practice. So there's not too bad, it's just be careful and be methodical. And these are problems that you just need to know a method. I like to know both because, like I say, sometimes algebraic is really beautiful, sometimes geometric is really beautiful. And keep at it because math is beautiful, right? All right, see you again.